Okay.
Okay,
Hello,
start.
everyone. Yeah, we can start. Hello, everyone. My name is Ajay Jacob, and I'm the Director of Projects at the California Dreams Hub. It's my pleasure to invite Dr. David Harame. He is the COO of AIM Photonics. Many of you know what AIM is. It's the American Institute of Manufacturing for the photonics. He is also the Associate Vice President for New York Creates, and he manages photonics, electronic-photonic design automation, test, assembly, and packaging technical areas. And he has been with AIM Photonics since 2019. And in his current position, Dr. Harame manages all the technology development in the photonics and packaging areas for AIM Photonics in Albany, New York, as well as in the Albany NanoTech Center in the Rochester, New York area for the test, assembly, and packaging facility. Prior to joining AIM Photonics, Dr. Harame was a Global Foundries Fellow and CTO for Development and Enablement. David was an IBM Fellow and CTO for Development and Enablement at IBM before joining GF. David Harame is an IEEE Fellow and received the IEEE Daniel E. Noble Award in Emerging Technologies for the development of manufacturable silicon germanium, HPT bipolar, and BiCMOS technologies. David is best known for his work bringing silicon germanium BiCMOS into manufacturing. David also worked on foundry enablement and technology development for RF CMOS, RFPD, and FD-SOI technologies. And he received his PhD in electrical engineering very long time ago from Stanford University. David, it's my pleasure to invite you to give this talk. Thank you so much to accept our invitation, and the floor is yours.
Okay, thank you very much for that kind introduction, Ajay. Okay, so it's my pleasure today to talk to everybody about AIM Photonics and New York Creates our PICs and packaging capabilities. So this will be this is a brief outline. We're basically going to run through these kind of topics, starting out with some essential aspects of AIM Photonics and New York Creates, who they are, what they are, and then talk a little bit about the technologies we have, focus on PICs, interposers, heterogeneous integration, and our packaging technologies, and with a little bit of electronic-photonic design automation, and then talk about our education workforce development aspects. So first of all, what is AIM Photonics? It's a Defense Department Manufacturing Innovation Institute, and it offers end-to-end solutions in photonic integrated circuits, interposers, heterogeneous integration, packaging, and EPDA. Now, we're part of New York Creates. New York Creates accelerates next generation technology research through its facilities, and it's best known for the 300 millimeter Albany NanoTech complex, which includes a Semiconductor Research Center that people are making 2 nanometer sheet transistors there, the Heterogeneous Integration Center, and the newest element, which is the High NA EUV Accelerator Center. So this site overall is about $25 billion of investment when you add everything together in the associated groups. The Rochester Test Assembly and Packaging Facility provides state-of-the-art capability. We'll explain all these aspects. But as an MII, we're really charged to advance photonics and packaging and particularly make all these advances accessible. So we're not really a commercial enterprise. We're trying to develop technologies and make them available and then educate people how to use them. So we have the educational aspects. Our latest efforts is really to work around building functional optoelectronic systems, things like co-package optics, etc. So first, let's just talk about New York Creates. It has 3 functions: R&D for advanced semiconductors. We just mentioned the center, ecosystem, economic development. It's really what the name stands for, and education and workforce training. Here's AIM Photonics. As I said, they have 3 functions, and we really have these 2 facilities. One is the Albany Nanotech complex shown on the left, and on the right is our test assembly and packaging facility in Rochester. So these are the 2 places where we build our facilities, and we're primarily a 300 millimeter photonic and electronic-photonic interposer facility. We do a lot of wafer level and chip-level simulated heterogeneous integration and packaging, both in the Albany NanoTech Center and at the test assembly and packaging operation in Rochester, New York. Now we do four things. We do PICs, and we've had a running MPW providing photonic integrated circuits since 2015. We have electronic and electronic-photonic interposers. We do custom packaging services and support a packaging roadmap. And we have electronic-photonic design automations. So the EPDA supports all of the PICs, the interposers, and as we discussed today, we're in the process of rolling out ADKs to support packaging. Now, I want to mention one thing about 300 millimeter. You get a lot of benefits from it compared to smaller wafers. I'm going to show you some data in a minute. But basically, it's just better alignment and much more uniform processes across the entire wafer. So we really benefit from this. And the Albany Nanotech Center in particular is a real center for advanced lithography. So it really is an advantage in our technologies because for the photonic elements, they may be large, but you really want very well-defined and smooth surfaces for lower losses and process control. And that's what we benefit from. This is actually a slide from AJ 2017, and it just simply shows this was a technology that was at Global Foundries. It was running in a 200 millimeter fab. They went to 300 millimeter, and you can see how it just sharpened up all of the controls on the wafers. There's some other material. I gave the reference here, but basically the net is there's a lot of advantages to being in 300 millimeter for photonics. And we benefit from that in an extremely strong lithography base. Now let's talk about the facilities that we leverage in Albany, the Albany Nanotech Center. So it really largely consists of three elements. It has the Center for Semiconductor Research. It's the North Fabs and these central fabs. And here's where this 2 nanometer sheet transistor kind of controls are. We have the Heterogeneous Integration Center, and we have what is coming up now, which is this what they call nanofab reflection, but it really is the site of the High NA EUV Center. It's a multi-tenant site, so that's another advantage actually of being on the site. There's IBM, there's Applied Materials, there's TEL, there's other companies that make semiconductor tools, and that really gives us an element of advantage because we work with these tenants for things like hybrid bonding tools, advanced packaging tools, etc. So that's another aspect working with us. You're gaining access to some expertise of the multi-tenant site in addition to just the facilities themselves. This shows the CSR, and the main aspect here is it's basically an advanced 300 millimeter 24/7 automated fab. It has a fully manufacturing execution system. Everything is tracked, controlled. Different tenants can keep their things proprietary. Leading edge lithography. It runs a production 65 nanometer to investigate different memory devices and RF CMOS, and basically just 24/7. So a lot of support to run the wafers. The next part is the heterogeneous integration fab. And here what we see is it has bonding methods. You can do TSV reveal. So the fab really takes wafers exiting the CMOS fab, and then you can go through enough of the packaging operations to singulate them and package them in Albany. So there is some duplication between what's in Albany and in Rochester. But there's this facility largely focused around packaging operations for 300 millimeter dense bumping. Now in our Rochester test assembly and packaging facility, this is a real general facility. We do a lot of wafer level operations. We have really 300 up. We're in the process of acquiring tools to be able to support more 200 millimeter operations. You can see lithography, PVD, plating, electrolytic, and electrolith, bumping, RDL, bonding, and solder jetting. So these are the wafer level kind of operation. Chip level, our busiest sector is really fiber attach and photonics. We do a lot of that, but we can do full advanced kind of packaging with die stacking, flip chip. wire bonding, assembly, solder jetting. This is an example of a LiDAR chip. The PIC was fabricated by us, and so this is an AIM Photonics PIC. And on top, you see 6 of these CMOS wafers. We actually got these wafers from a foundry, bumped them, and then flipped them. So there's 3,000 times 6 bonds, full, 100% yield. So in addition, we have failure analysis and test on site to debug processes while we're doing development. And we have some advanced tools coming in, particularly largely focused around photonic and optic kind of packaging processes. Here we're doing a microtransfer printing, photonic wire bonds, so we can use 3D printing to create lenses, die-to-wafer hybrid bonding, wafer reconstruction, etc. So these kind of processes the wafer reconstruction is still in development, but the other processes we're getting tools, putting on site, and have been doing these operations. Let's talk about the MPW. So we really think that by having the PIC and the interposer processes in-house, this gives us a real advantage for end-to-end kind of development for things like co-package optics. For one thing, you want to be able to modify the PIC to get the most out of a full co-package optics kind of offering. We've been running the base MPW since 2015, so it's very mature. It has multiple component libraries, and some of them have statistical models. There's other ones that are lower level. We communicate that to you, so you could pick up components developed of different maturity. We have a passive where we've removed the implants, the metals, and the germanium. This actually was one of the primary elements used for COVID sensors during the pandemic. And since then, we have developed a very low loss silicon nitride platform, which is being used for sensors. There's a near IR and a visible aspect to it, and it's being used for some quantum aspects as well now. So this is a very low loss platform. And you can see here we have electronic interposer. We're in the process of doing electronic-photonic. Now it's really important if you have MPWs that you run with, you just constantly run. So it's not like we'll run or not depending on how many writers we get. So you can see here, these are our silicon nitride, the passive, electronic interposer, the full active, and we run these quarterly. One aspect that differentiates us from large foundries is the ability to do customization. You can sign up, and when you do your purchase your MPW, you can actually sign up to modify different processes. Now, there are additional costs for this. A wafer has to be pulled out because all of the customers may not want to get the customizations that you want, but you can change metals, you can change implants, you can change thicknesses, and that flexibility, I think, really distinguishes us. And there's a lot of new emerging applications in photonics, and developers really want the ability to modify the process to optimize it for those emerging applications. So let's talk a little bit about the PIC offerings. And when we orient towards the PIC offerings, we think of ourselves as having some application, some generic application-specific platforms for the PIC, and then we develop heterogeneous operations on top of that can go across any of these other platforms. So we'll explain that more in a minute. So here's the photonic applications, the platforms we have. So you can see this is this base MPW. It's been running since 2015. We now have a second version of it, which is driving down losses, improving performance. We have silicon nitride. So this is heavily used for sensors, but now also being used for more visible applications and quantum. We have a full silicon photonics for quantum. This is quite different from the base. It was completely redone from the ground up. It has different implants and optimized, very low loss. You can see here is a single photon emitter entanglement device. The idea here is that we will not only have this generic offering for silicon photonics, but I'll show you later, we're going to add elements, and you'll be able to come in and pick up quantum optimized cells for silicon photonic. And then we're working on integration of 3.5. There are many different ways to integrate 3.5s. We'll talk about that a little bit in the talk. But one way is heteroepitaxially, we're working on this because we think it's the densest form of integration. And you can see here, this is on our 300 millimeter wafer. The end processing was actually done in a cut down version at UCSB, but this was all 300 millimeter processing to grow the epi and make contacts. And you can see here's a fully functional laser on it. These are quantum dot lasers, O-band. So here's the interposer platforms. The first is the electronic interposer, and there really aren't a lot of US-based interposer offerings. And you can customize this again. It has TSVs. You can the metals, how many metals you want, etc. And we do have other elements here that have been enabled: capacitors, resistors, inductors for passive kind of devices. Here's the electronic-photonic interposer. So we take this and basically flip the MPW full silicon photonics on top, remove the backside, and wire these things together. I'll show you for some slides later on. This is being redone a little bit. These connections are being replaced with hybrid bonds for low parasitic connections between the two. There's a lot of interest out there in large area interposers or substrates with waveguides on the surface. And these are low waveguides and a fairly mature offering. You get the silicon photonic devices in addition. And very early on, when AIM was actually started, this was done initially with CMOS wafers. So you could do CMOS here as well. These are our packaging platforms. So we've broken our packaging platforms into 4 areas. And again, we do packaging in Albany NanoTech HI Center and in the test assembly and packaging facility at Rochester. So we're able to leverage the more dense side in Albany and the generic side in Rochester. So here you can see wafer level operations, 300 millimeter PVD, lithography, plating, etc. If you take a look at the assembly package, we simulate devices. We do plasma dicing, laser dicing, mechanical dicing. We can build up different covar substrates. We can place things in different packages, wire bond, flip the chip, or we could, connect fiber. So there's a lot of assembly done. We're working on reconstituted wafers. It's not quite there yet, but we plan on offering this. And then we have a fairly large area focus on optical coupling. We'll describe that in a minute. So here just shows you some of the characteristics of our 300 millimeter base MPW. We have a inline tester. We do wafer acceptance criteria. We measure every wafer. It just shows you here was the first version. You can see we've reduced the losses in the second version. And again, every wafer goes through and is characterized in line. This happens to be a Tel Precio with a lot of Keysight characterization equipment on it. We're now going a level above this to actually include visible. You can't really just go out there and buy an inline visible tester. So we're custom developing this with our collaborators. This is our silicon nitride platform. And essentially, I'd mentioned that in our full photonics, when we remove the implants and metals and germanium, you can run this as just a passive. But the NRL laboratory came and said, listen, we need to really drive these losses down, very low fluorescence and less coupling to the substrate. So they told us what they were doing in smaller form factors, and we collaborated together to implement that in a 300 millimeter offering. So this is now, they're running all their stuff with us now, essentially. And we're now driving this towards shorter wavelengths, more visible, and also adding heaters here. We think this will be a very interesting platform for sensors and quantum, etc. Here's an example of what we did with the passive. This is a COVID-19 biosensor. You can see we have these rings. There's a control and one with absorbate, sensitive to COVID antigens. And you can see here the control, no signal. And you can see this rising signal here for the positive. So this was early on. This was done with Ben Miller at University of Rochester. They've extensively published in this, and they've also actually generated a startup, Photonics. It's also SiPh using us. So there's other companies now that are coming to use us to take advantage of our sensor platforms. Now let's talk about quantum. So we developed our quantum platform jointly with AFRL, RIT, Columbia. There were several people, several groups that contributed to this. This shows a MPW in the technology. By the way, the government has really been interested in this, and this has also been swept up into the Microelectronics Common NorTech Cup. NorTech is known as QFlex, I'm sorry, QPICs, Quanta Ultra Broadband Photonic Integrated Circuits. Here we have QFlex and AIM Photonics. You could come in and run an MPW. What we see here is here's some of these single entangled photon sources. And again, you're going to be able to come in and pick this up as an IP block. And if we have done various cavities and exposed waveguides, here's an example showing a lithium niobate device. We have the ability to do cavities underneath active devices for thermal optic phase shifters and other aspects, so you can thermally control devices. Here's an example where we actually did some photonic crystals. Let's go back to the comments I made about lithography, just the 193 immersion that we pervasively have. I mean, we basically patterned all these, and light propagating through these just has different properties. So this is also a capability. It's a custom thing. It's not generically offered, but this is, we're able to do this. And just some other things. Here's our losses that are in the platform. And we're in the process of developing alumina nitride, alumina and thick nitrides. So that's shown here. This happens to show that we're doing this in 3 phases. Today we're doing phase 1, which is just the straight silicon photonic. Phase 2, we're going to expand different materials. Here we show alumina and alumina nitride being offered to the full silicon photonics platform. And then phase 3, we're going to add thick nitride for combs. So we think this will be a really interesting offering, and it's being used now in Microelectronics Common NorTech and also across our in photonics quantum activities. Quantum's a really big interest. This just shows some of the fact that we have these cavities that we remove silicon for just to make a much better control. We also control different aspects of removing silicon underneath edge couplers in order to get lower loss. So again, this platform is available today in AIM under QFlex and microelectronic QPICs, and also there's a quantum networking NorTech project that's also using it. So we have both of these in the Commons. And the Commons actually has, we've actually got sponsorship from AFRL in order to offer an MPW. So it's a generic offering for anybody in the country, and you can submit. We're now doing this once a year. We've got one running now that should be out in a couple months. Here's our 3.5 integration platform. What we have here is the ability to integrate lasers, quantum dot lasers with silicon photonics. So this is kind of a cross section of the device cartoon here. You can see the full silicon photonic offerings, the metals, and here we have etched down into the substrate and actually growing this laser, quantum dot laser. You can see all the different layers. And at the center here, we have quantum dot layers that are formed, and that's the part that's doing the emitting of light. Okay, this just shows an example where we have fabricated these lasers and coupled them to passive elements. In this case, we have some silicon rings and DBRs for filtering, so we can control, move the wavelengths where these dips are occurring. And we can also take these lasers and sort of operate them in a different mode. And yeah, and then we have photodiodes. So this just shows an example of a photodiode where we've done exactly that. Now let's talk about the interposers. So interposers are particularly interested. We've supported electronic interposer in a lot of custom builds, and now we're really rolling out the electronic photonic interposer. And again, this has the ability of putting different wafers underneath here. It doesn't have to just be the electronic interposer. This is an example of an electronic interposer. You can see we built the interposer, we simulated it, we made it so it's accessible for bumping. We formed bumps and attached electronic IC to it, and then the other side attached it to a PCB. So this just shows an X-ray of it, and you can see cross section here of the devices here, and what this is. So it's an example of a build that we can do. Let's talk about lasers. So there are many different ways to attack lasers. More conventional ways is just to either bring them up with free space optics or through fiber, butt coupling, or however you're going to do it. People are using photonic wire bonds. We're in the process of developing that. We do a lot of 2.5D flip chip. This is something we're going to be offering in the MPW. So probably roll this out this year in June, and later in the year, you'll be able to, in your MPW, order as a different component, an actual 2.5D laser. Initially, it'll be C-band, and you'll be able to put that cavity in and have light sources on chip. It's just part of our MPW offering. And you can see we just talked about Lumos, where we've been monolithically growing these. And we have not done hybrid as an offering, although we are doing projects heterogeneously attaching 3.5 coupons. This just shows the 2.5D laser work. This is an example. This is a laser. Actually, we acquired this. Sorry, that thing keeps popping up. We acquired this from Freedom. And so we have lasers, and we define the element, the cavity here, and it's just an edge coupled at the end of the cavity. This just shows you an LIV curve from it. And this has a full PDK element. So you're going to be able to come in as an MPW and just place this and be able to have light on wafer. So let's talk a little bit about coupling. Many different ways to couple. You can do it with gratings, and we offer a variety of different gratings. We have edge coupling, and here we get particularly low loss by removing silicon underneath, and of course optimizing the coupling structures. We're now in the process of developing evanescent coupling options. We're printing micro lenses, and we actually are doing that with a couple different 3D printing vendors, photonic wire bonds, and we have not done a free space polymer yet, but I think that's going to be coming as well. So users that are interested in having AIM fabricate things, I think we have a variety of different ways for you to get light on chip. This just shows a grating, for instance. You can see there's some advantages, especially for wafer level test and getting in and out easily. The grading disadvantages, high coupling loss, etc. But there's a variety of different gratings, and we're constantly improving the performance of these. This shows edge coupling. What you see here is a structure where we have actually gone underneath the waveguide and removed silicon. So you can see in cross section, the edge coupler is coming here and the silicon has been removed. And that enables us to get very low losses. Okay. Here's some example of some other coupling work that we're doing. We're printing micro lenses. We're doing evanescent coupling. And we're also doing other kinds of devices just to get better optical couplers performance. So let's talk about packaging. These are the different kind of packaging operations. We have a lot of 3D wafer to wafer bonding. We have not yet. We have tooling really on site, and we're going to be starting die to wafer efforts both in Albany and in Rochester. So we have extensive wafer to wafer, bond to bond, and have already started some of the die to wafer work. So hybrid bonding, this shows 1 micron pitch that we did. Again, going back, we have some advantages because there are vendors on site that are developing tools for this, and we work with them. And here's some 2.5D placed lasers here. We also have PICs that were placed here in this example, and dense bumping. This shows 23 micron copper pillar. Here's 50 micron copper pillar with 10 silver caps. So we have this offering both in Albany and in Rochester. This is a little more description of our TAP facility in Rochester. So again, it has 300 millimeter wafer level, chip level assembly, metrology, and test. This just shows you a couple pictures of the facility. Here's some examples of builds we've done. So incoming wafer, we bump it, we simulate it, we flip chip it, we may build some sub mounts and other things. We can do wire bonding, fiber attach, and then we can test it on site. So there's extensive test capability. Now, it's really important that we're able to do enablement. So early on, we started doing PDKs. And one of the aspects of our PDKs is for each technology, there's a PDK, and then there's multiple component libraries that you can use. So when you get PDK access, you go in, you pick your technology, and then you can select from different component libraries. There may be very mature ones. They might come with some licensing, commercial licensing restrictions. There's some RF SUNY provides. Most of those devices are really open. And there's some other, we call them crowdsourced or application-specific elements that we've assembled. We're also working on a measurement design kit. So what this is basically a layout setup. So if you copy these layouts, they're immediately compatible with our test setup in Albany and in Rochester, and then you can test the device fairly simply. And then the real activity now is on the assembly design kit. Here we have some comments about ADKs in general. So the CMOS industry is extremely mature, right? Verification, sign-off, PCB design, interposer, all these different aspects are just routine in the CMOS world. Photonics, optics, not so much. So we're trying to, especially with ADK and other aspects, drive putting these steps in place just to mature overall the photonics, electronic photonic design automation. Here are some examples of where people have used our EPDA. This is our quantum technology. It kind of shows all these components, which are in the PDK. People go in and they can use this to design different elements. Here's an example of one element, a vertical junction ring modulator. And then, they build some circuits and it shows it. I want to make a comment here about the EPDA here, which is, a lot of these electronic photonic design automation providers, they have what they call layer builder files. So what we've done is gone in and worked with these vendors so that the detailed process information is encrypted, but you have access to simulate with the real end profiles. And there are documentation gives you a lot more information about all of the different dopant levels that are available, kind of sheet rows, center of the centrus of the dopant profile. And then when you simulate by using this layer builder file, you can actually simulate with the real dopant profile. So we think especially people that want to do custom development, that's a big advantage. I don't know that any of the large foundries are offering that. So we've gone out of our way to try and be multiple vendor kind of support. Here you can see our premier platforms are Synopsys and Cadence, but we also have K-Layout, and we've also implemented K-Layout DRC, and then a host of other things, including GDS Factory, Luceda, of course, ANSYS, Lumerical, that's extensively supported, and Tidy 3D. So I would say for each of those technologies, not only are there multiple component libraries, but there's a pretty large suite of EDA tools that you can use. So let's talk a little bit about co-packaged optics. This just shows that there's several different ways of getting bandwidth up. One way is just by the number of lanes. You can just have a lot more fibers, a lot more wavelengths in fibers. You can have your modulators run faster, or you can have more complex modulation. So you put all these things together. We're trying to enable the ability to do this. I'll show you some examples. Obviously, the integration. bringing the components closer into the device to reduce electrical connections and bring the optical connections closer is also a large element of getting a better performance. This is shown here. This is an article by Margalit, the John Bowers group. And what you see here is more pluggable optics. You can see the pluggable optics around the faceplate. These still exist, but there's longer electrical leads that go into the switch IC. The next step was to try and take these pluggable optical transceivers and put onboard optic modules. This shortens the metal lanes, so reduces the delays. Then there's 2.5D, where you're taking some of these optic modules and placing them in the same substrate. And the package substrate, you're doing 3D co-package optics, where you're stacking these different elements. And then we're working again on actually fully integrating the laser elements into the technology, not just with 2.5D, but heteroepitaxially growing it. I might add that Intel is an example of somebody that they use a coupon approach, but they're also doing the same approach for co-package optics. This is an example of what we've been doing in co-package optics with one of our collaborators. This is Karen Bergman. She's done this work, Broadcom, Cisco, Juniper, Arista. And what they had here was they took our photonic integrated circuit platform. They developed custom modulators. So these are very low power modulators. Anthony Rizzo, who was at Columbia, went to the Air Force, now is at Dartmouth. He's published extensively on the work done on our PIC platform. But you can see, take a comb laser. This goes in to a lot of wavelengths. You're really modulating, selecting and modulating each of those wavelengths. And then, of course, after you transmit it, you have to have the receiver. In this case, you have filters and then photodiodes. So Karen Bergman, I believe, holds the record for the highest bandwidth, lowest power. And this was based on our technology. This is our test and measurement structure, which just shows you a little bit about what you can do at what site. This is, we have an offline lab in Albany. Our test assembly and packaging facility in Rochester has a measurement lab. And then, of course, we have inline. So this just shows some of the different measurements that you can do. Now, one of the aspects about the measurements, if you're in Albany NanoTech, that's like over a $20 billion investment. So you can't really have customers come in and run tools on their own. It's not really a user facility. But the measurement lab's a little bit different, right? So we're and the tap facility is also different. We're, if there's an effort that you'd like to have people come on site and participate, particularly in the measurement lab, we have that. And there's also some opportunity, depending on what the agreements are, to do more like in the test assembly and packaging facility. But the test facility will work with you. It's easy access to a lot of equipment, and particularly if you use the measurement design kit, you could gain immediate access to it. So we're going to be kind of closing the discussion here, talking about education, workforce development. So there really is two parts to this. One is the New York Create side, and one is AIM Photonics. The New York Create side has really focused around technician training, and they actually train the technicians. Global Foundries has a large fab in Malta, and actually New York Creates is training technicians for them. And they've had they're interested in STEM, and they've had a large footprint on this. So that has been ongoing, just general. But if you take a look at AIM Photonics, we've got several different ways to teach photonics. I would say the one that's had the largest impact has been our online courses. So to date, we have our PIC 1 course, and then there's a series of other courses. There's PIC 2, there's one on sensors, there's one on ring design. These things are all online. The PIC 1 course has had literally over, I don't know, maybe it's up to 10,000 now participants. Now, not everybody takes the full course and actually lays out an integrated circuit, but you can take this course. During the course, you learn about, how to build some devices, and you tape out a chip. They take the best chips and aggregate them, and we run them. And then in a test course, you can actually test those chips. So we have for hands-on, we have packaging workshops and test workshops in Rochester. There's a Semi Academy that's held at MIT. We have internship and co-op programs. Educational development, we have Reach Out. We're trying to do more for STEM. And one of the things we've been doing is developing a syllabus or a platform so that universities can have their own kind of photonic course offerings. And they can do it by actually taking real photonic circuits and offering students the capability of testing those. So we call this hands-on photonic education. You get one of these kits and it's fully enabled with a full syllabus. There's like 6 different modules, and you can use this as a bring up of teaching photonics in the university. So I would say in net, I kind of talked briefly here, briskly, so I'll be open for questions. But essentially, AIM Photonics is a manufacturing innovation institute. We offer end-to-end, so we're really trying to give you the ability to design the PIC, your interposer, custom packaging, and be able to test them and support everything with electronic photonic design automation. We really benefit from the 300 millimeter Albany NanoTech complex. The lithography there, capabilities, that's just alone is just amazing. And the tools have to be very uniform in order to support things like 2 nanometer sheet transistor development. And we have all of the on-site vendors that we also collaborate with in next generation technology. So this is a big advantage for AIM Photonics. You're getting access to those by just running in our MPW or custom runs. Then there's the Rochester Test Assembly and Package, which is a very focused more around the photonic packaging. It's not in the CMOS fab. So there are some materials you cannot run in a CMOS fab like lithium niobate. Those things are all heterogeneously placed or run in Rochester. So we did give the capability of doing different types of materials. So we're missioned to advance photonics and packaging, make it available, and build a skilled workforce. I think our education programs have been particularly successful, and invite people to look into them if they want to learn more about photonics. And we've put a lot of efforts on end-to-end and building co-package optics and addressing some of the challenges in photonic packaging. And that's basically it. So I'm open to questions. Thank you very much for your kind attention and interest.
Thank you, David. Great. It's a lot of work happening at AIM Photonics. Lots of information you tried to conceptualize, put it into 40 minutes. Any questions? There are some questions, I guess. Siwai Sung has 2 questions. Siwai, do you want to take the mic and ask the question?
Yeah, my question is, is the PDK include weather or environmental parameter? For example, like a temperature affect wavelengths and output?
Well, yeah, that's a good question. I think the components are largely OCL. Obviously, there has to be some thermal for thermal optic field shifters and effects of the temperature. I don't know that there's, I actually don't, sorry, I can't really answer the questions about how much thermal is in the models. There's some in probably the more mature offering that's Act 1. And I think that's an interest where people are, well, that's an area of more interest. So we're probably going to be including more of that. But I think if you look at the more mature offering, the base, that there's some thermal effects in there as well as different wavelengths, but just OCL for that. For the more visible and different wavelengths, that's going to be supported across the quantum platform, the QFlex, and the silicon nitride platform.
Thank you.
Did that answer the question? I can get you more information about that, what's in the compact models, if you give me some, send the question.
Okay, thank you.
Any other questions? Oh, there are 2 other questions. Anshu, You want to take the mic and ask Anshu? Anshu Bahadur from Semi.
Excellent presentation. A lot of information, as Ajay said. One is SEMI is an industry body, and we're doing some work in CPO and packaging. Would you be open for a reach out or connect with us?
Yeah, 100%. You bet.
Okay. And is it possible to get a copy of the slides if I can reach out to you on that?
Yes. While the webinar is being recorded, I can give a copy of the slide to AJ. He can distribute them.
Yeah,
Thank you.
this webinar is being recorded, and you can watch the webinar in the YouTube. You can go to California Dreams YouTube site, and then you can watch it.
Okay. And David, your contact information
the next
is somewhere
question,
on. Your contact information will be somewhere on the AIM4 website, right?
Yeah, I think my last name is HARAME. My user ID is dharamy@ny-creates.org, and that's on the website. And I'm sure Abe, if you ask AJ, he can give you that information as well.
Thank you. Thanks. Thank you.
Yes. Dave Carras has a question. Dave, do you want to take the mic and ask the question? Okay. Dave's question is, can you describe your TSV offerings? What kind of dimensions and
Today we have 10 by 100. But we have a TSV scaling program. We're driving more towards 50 micron and trying to shrink the length as well as the width below that. So we're currently working on TSV scaling. That, of course, requires some wafer thinning scaling as well, right? So we have a program in place right now that we're doing. Today it's really kind of 100 micron width, 10 by 100. Oh, sorry, 10 by 100. Did that answer the question?
Okay. I think so, 10 by 100. The next question is from Sripriya. Sripriya, you want to take the mic and ask the question? Okay. Let me ask the question. So she says, great work, David and Aim. With current facilities, what kind of maximum wafer volume can the Q-Flex and passive silicon nitride process flows? Similarly, what is the capacity of TAP facility?
Well, you asked kind of two questions there. TAP is packaging, so I think we can do low volume production there. Yeah. In terms of the wafer fab, what I like to say is we have sort of a 10, 100, 1,000 kind of approach to it. So if you come and you want 10 wafers during a year, we can easily accommodate that. If you want 100, we have to expand a little bit the footprint, but that's not difficult. We have a multi-use fab, right? So we have a portion of the fab that we possess. If you start wanting more than like 1,000 wafers a year or so, then we'd have to, on your advocate, negotiate for a kind of part of the activity in the fab. That's possible. So I would say that there is a possibility to go from lower volume to higher. There's some that are just going to be immediate. Some we just have to get our slice of the pie expanded to support, and then even beyond that, we'd have to go to the organization that runs the fab, which is actually New York Creates. So we're kind of part of that organization. But anyways, we could also, that's also possible. Did that answer the question?
I think so, yes. Any other questions?
Yeah, I have a quick one. Are you able to compare between 2.5D and direct bonding and the monolithic, the thermal management difficulty?
I didn't hear the last part. I heard you compare 2.5D and monolithic, but I didn't hear the last part of the question.
2.5D hybrid and monolithic and the thermal management comparison.
Well, that's really a good question. By the way, one of the aspects of building the laser by heterogeneously growing it is on the silicon. So it does kind of provide a bit of a heat sink there. Obviously, 2.5D, is going to have some concerns there, depending on how it's heat sunk. We're in the process of rolling these offerings out. We hope to have the MPW. We're currently for the 3.5 growth. We've got about 11 riders on that, and hopefully we'll have our fully functional 300 millimeter offering coming out in September. We hope in 27 to be offering an MPW. I don't have a lot of information right now on a comparison across, but that's a great question. And I think that's something that we need to do is kind of publish a comparison of the three in terms of thermal. Of course, depends a little bit on the 2.5D device that's being offered. We're putting 2.5Ds using microtransfer printing and with thinner devices and some thicker ones in the more conventional 2.5D. So there's a couple different ways to do that, and of course the thermal behavior will be different. That's something that we need to publish more extensively on. We've not done that yet, and I think that's a great suggestion. Thank you.
So you don't recommend one more than the other, right?
Well, I think it's a question of what you want to do long term, right? Let's say that tomorrow we had the 3.5 growth, so you could really look at the 3. The first thing is that if you have 2.5D, you're paying per placement of lasers, so to speak, because there's some time consumed there. So it's not really scalable if you need to put tens or hundreds of lasers on each chip, right? There's just a lot of placement there. Now, microtransfer printing gives you the capability of possibly putting many elements in the same one. People actually use this kind of technology for displays. So they have proved that these kind of technologies can be used for replacement of a lot of devices. But I think the ultimate is really the growth, right? Then it's like a regular semiconductor process, and you grow them everywhere on the wafers. Yeah, we're pursuing this because we want to have dense integration of SOAs and lasers, and there you wouldn't have the restrictions of the time-consuming part of placing each individual device. Did that answer
thank you
the
so
question?
much. Yeah, thank you.
Great. Any more questions? I have a question, David, and it's very simple. It's excellent presentation, but how do a user access AIM facility? Is that information on the website, or how do they approach you?
Yeah, thank you for that question, AJ. And yeah, we have AIM Photonics, a website. You can just go straight onto that website. There's a section that is for MPW, and you can go in and request a PDK and put your information in there, and then you get access to the PDK. You can design it. All of our prices for all of our MPW offerings are on the website. It's more limited for packaging what's on the website, just because there's a lot of custom kind of packages that people need. But the way you engage with the packaging side is basically put in an inquiry. Hey, I'm interested in some kind of a services agreement to do some packages. We get back to you. We sit down and go over your statement of work, what you want packaged, and then we give you a quote. So it's pretty straightforward and can move pretty quickly. So both sides, the MPW could be, you could just get a PDK and just do it. You don't have to be a member or anything. If you want more custom, a lot of people come because they want some customization, and then you can either do this bite-sized custom if it's more limited, where again everything's priced and everything's apparent on the website. If you have a more custom development, and we do sponsored projects and do custom development, we would have to agree on a statement of work in order to understand what you need, and then we would implement that. The packaging, it's just put the inquiry in, we'll set up a meeting. We kind of traffic in cartoons. You got to give us a little bit of a cartoon, your build, what you need, what your pitches are. And we're trying to do these 80Ks so we get out ahead of you. So when you design PICs or EICs, well, you can design them to make sure that we can actually package them. So we'll help you do that. It's almost a syllabus of packaging when you get our design equipment. But basically, you just interact with us, and we'll go over your packaging build and give you a quote.
Thank you.
Did that answer the question?
Yes. Thank you. So is there any more questions? Okay. If not, Thank you so much, David. It was a great presentation, and thank you for your time. Thank you
Thank you
everyone
very
for
much.
attending.
Thank you, everybody, for hearing. Thank you. Okay, bye.
Next week's presentation, go to the second slide. Next week, it is Alexander Janta Polsinski from IBM Bromont. Thank you.